All right, lesson 29, a surprising boost from geometry introduction to complex numbers. Um, we're going to try to explain this in a couple of different ways to see if we can kind of grasp or grab a hold of this thing. There's a video on YouTube, if you want to look it up, that gives an animated explanation, which might be a good way to go. I won't do that here just because you can look that up if you're confused. All right, so the opening exercise I've already done for you just to sort of speed things through. Clearly, we've got x equals 1, x equals negative 1. We can solve these equations, x equals both plus or minus 1. But what happens when you have x equals plus or minus the square root of negative 1? Up to this point, we keep saying that we can't do that. There's nothing we can do. But there is. So um, from the time of ancient Greek throughout Renaissance period, mathematicians were also perplexed by such problems. So uh, Cordon considered a problem, and as you work the problem out, find two numbers, a and b, whose sum is 10, right, and whose product is 40. So I've got a system of equations here, which you guys can solve. I'm going to solve by substitution. And as you get down to it, you end up with this quadratic equation. Well, we can manipulate that. And then we look up here to see if can we factor it. No, it doesn't factor. So my choice is, do I want to complete the square or do I want to use the quadratic formula? Some would use the quadratic formula, which is fine. I completed the square. By completing the square, I end up with an answer that says 5 plus or minus the square root of negative 15. Well, the square root of negative 15, again, is another one of those situations that we've been avoiding. Today, we're going to see if we can explain that. We start with the whole concept of a number line and multiplying by negative 1, right? When you multiply 2 times negative 1, you end up over here at negative 2. If you multiply negative 2 times negative 1, you end up back at 2. Kind of a circular argument here, okay? Same is true for uh, imaginary numbers. And they're saying that if I have uh, the square root of negative 1, if I start with 1 and I multiply by the square root of negative 1, I end up with what we call an imaginary solution, right? That goes here. If I multiply by a square root of negative 1 again, so we had 1 times the square root of negative 1, they're saying is equal to I. If I take that square root of negative 1 and multiply it by the square root of negative 1 again, right, isn't this I times I? And they're saying that that's going to rotate and become negative 1. If I take that negative 1 and I multiply it by the square root of negative 1, I get negative 1 times I, which becomes negative I down here, right? If I take that negative I and I multiply it by the square root of negative 1 again, that's going to be negative I times I, right? Which becomes 1. Kind of an interesting scenario. Now this is just I. This is going to be I squared. This is going to be I cubed. This is going to be I to the fourth power, in case you're looking at it in that notation. Um, we're mainly going to be looking at I squareds. Notice that I squared always equals negative 1. All right, so um, I'm going to keep moving here. When we perform two 90-degree rotations, it's the same as performing a 180-degree rotation. So multiplying by I twice, you get the negative 1, which is what we were showing before. Um, that's just the square root of negative 1. Okay. So we know I was the square root of negative 1. We know I squared is 1. We know I cubed is negative I, and I to the fourth is 1. Now, interestingly enough, we can play around with all these, and we can keep going all we want. Um, this is something you probably should try to understand. As we go through, I'll fill this in quickly. Okay, so the first four we had already done before. Now, what's interesting is that I to the fifth is just going to be 1 times I, or I. I to the sixth is going to be 1 times I squared, which is negative 1. I to the seventh is 1 times I cubed, which is negative I. And I to the eighth is 1 times 1, if you will, or 1. And if we keep going, I, negative 1, negative I, and 1. What we're finding is that anything with a even exponent that is divisible by 4 will always be 1. And from there, we can always manipulate and decide if it's I, negative 1, or negative I. So I to the 23rd is close to I to the 24th, which is divisible by 4, which we know that is 1. So in turn, this is the one here that is just before 1, right? If you will, this is I to the 20th times I cubed. We know I to the 20th is divisible by 4, so that's got to be 1 times I cubed, or 1 times negative I. That's going to equal negative I. Long explanation. All right, let's try that again. I to the 57th. Okay. I know I to the 60th is divisible by 4. I know I to the 56th then is divisible by 4. So this is equal to I to the 56th times I, right? Or 1 times I, which ends up just being I. We can pick any number on the number line and put it as an exponent, and we should be able to simplify using this pattern. Keep in mind our focus here is usually it's gonna end up being the I squareds, um, just so that we can work with quadratics. All right, remember this one, the first exercise, where we had x squared plus 1 equals 0, so x squared equals negative 1. Therefore, we ended up with x equals plus or minus square root of I, or square root of negative 1, or x equals plus or minus I. Now, we want to prove that, right? From our table before, if it was I squared, that would be negative 1. If it was negative I squared, negative times negative is positive, I squared would still be negative 1. Negative 1 plus 1 is 0, and so we have proven that this is true. All right, we are looking at specifically here complex numbers. This comes in the form of a plus bi. Our a is our real, our b is our imaginary, and notice that we ended up with two answers. Um, these imaginary numbers come in pairs. These complex, these are complex numbers. They always come in pairs, a plus or minus bi, if you will. All right, so I'm going to skip over this chart. If you need to stop the video, take a closer look at this. They're just asking a look to see what is the real, what is the imaginary portion of these. And it gets interesting down here. Um, Clearly, your complex number didn't have an I in it, but it's still considered a complex number. In your number system, complex numbers are an all-encompassing portion of that. All right, this is where we need to go. We need to start simplifying. Uh, Keep in mind, for if there's a negative under the radical, always pull out the negative, right? That negative becomes -1 times the square root of 24, which is I times square root of 24. You guys can simplify. That's 4 times 6. We know this becomes 2 square root of 6I. Quite often I put the I on the other side just so it doesn't look like it's under the radical. You'll see it as 2I root 6. This is the appropriate order to put it in, but it's easier to read here, so you're going to see that quite a bit. We're asking you to simplify these things. Part B, again, you're dealing with the 75. So off to the side, you might consider going, well, I know that's going to be I times the square root of 25 times 3, or 5I root 3. So over here, this is 5 plus or minus 5I root 3 over 5. You can factor out that 5. 1 plus or minus I root 3 over 5. That allows you to cancel the 5's, and we're left with 1 plus or minus I root 3. Now take a close look at this, because the common mistake here is to cancel these, either only one or cancel both, and then not have that there at all, and that one would disappear. That is not correct. Factor that 5 out. Make sure that there's a 1 in its place, right? Because 5 divided by 5 is 1. That's what happens when you factor. And again, notice that you end up with complex numbers. I'm going to let you stop the video and finish these up, see if you can come up with the right answers. All right, so take a minute, check your answers. Make sure that you are, when you factor out, you're leaving that 1. Okay, when collecting like terms, this goes back to our basic algebra skills, in that um, we're looking for common factors to put together. In this case, there's x's, there's y's, there's whole numbers. I'm going to let you play with this. I'll put some answers up. So stop the video and work some problems. You can collect like terms. All right, just to clarify, we can solve for x and y knowing that these are equal, and then put together your complex number. Okay, so if you isolate the x's and y's, you can solve for x's and y's. C was a little more complicated in that you had to distribute and then organize your x's and y's. The discussion continues with graphing complex numbers. You've got your real axis, you've got your imaginary axis. And notice that the plus or minus -1 plus or minus 2i, -1 plus or minus, they're going to be vertical from each other. And again, here's a situation where I use the quadratic formula to solve this. And our summary says, hey, a plus bi is what we're looking for. Square root of -1 is equal to I. Good luck. Let's have some fun.